fixed 0. If we try to see how much this address now is funded, it's back down to 0. Awesome. You've now learned how to deploy a relatively simple yet effective crowdsourcing application where users can fund and an admin can withdraw those funds to go spend them on things. Now, we've been working with Remix so far to start our smart contract and our Solidity development journey. Remix is an incredibly powerful, what's known as a web IDE, or an integrated development environment. And in my opinion, Remix should always be the starting ground for anybody looking to start their smart contract journey, because it is a wonderfully friendly way to really show what's going on behind the scenes. And it's really easy to see everything we're doing with Ethereum, with Chainlink, and with our smart contracts. Now, it does have some limitations though. It's really hard to integrate other parts of different projects. It has some limited support for testing or custom deployments. It's a little tricky to save files locally. You need an internet connection to actually interact with it, and it doesn't have Python. So in order for us to deploy, test, and automate everything about our smart contract development cycle, we want to connect our Solidity and our smart contracts with a more traditional programming language like Python. This way, we can customize our entire development environment in any way that we like. We're first going to teach you all how to work with what's known as web3.py, which is an incredibly powerful Python package for doing everything that we want to do with smart contracts. Then, once we learn some of the basics of web3.py, then we'll move on to Brownie, which is a smart contract development framework built on top of web3.py, which makes our lives even easier. However, it's still really important to learn web3.py first, because this will teach you what's going on behind the scenes of Brownie. Now, for the rest of this course, I'm going to be working with Visual Studio Code, which is an incredibly powerful text editor that will give us a lot of formatting and a lot of really nice tools to work with deploying and interacting with our smart contracts. If you've already got VS Code and Python and your entire coding setup set up the way that you like it, feel free to use the timestamps in the description to skip ahead to the next section. You'll often hear people referring to this as VS Code or Visual Studio Code. But just to point out, this is not what you're looking for right in front of you here. Visual Studio is a different application. Make sure you're on Visual Studio Code. If you want to be a total hardo and just work with Vim or Emacs or whatever else you want to do, you absolutely can, but I'm going to go through setting up Visual Studio Code the way that I like it. And if you guys want to follow along, I highly recommend it because it's going to make your life a lot easier. There's a link to download Visual Studio Code in the GitHub repository. Basically, all you have to do is come to the site right here and you can hit this big download button. It should recognize what operating system that you're on, be it Windows, be it Mac, or some other operating system. And if it doesn't, you can go ahead and hit this little drop down and pick one there. So let's go ahead and download Visual Studio Code and open it up. Awesome. Once you've downloaded Visual Studio Code, this is approximately what you should be seeing. There's a fantastic getting started section here where if you're brand new to VS Code and you want to learn a little bit more quickly, you absolutely can. And we have some links as well in our GitHub repository, giving you a crash course in VS Code if you want to learn more. Let's set this up though, so it's going to be really friendly for us to be doing our smart contract development here. So first, we want to go to this extensions tab. It looks like these little blocks thing right here. And first, we're going to look up Python, and you want to install this Python extension right here. This is going to make our lives a lot easier for interacting with Python and doing a lot of things with Python. Then you're going to want to go ahead and download this and install this Solidity extension. This is going to make formatting our Solidity a lot easier. Now we want to download Python if you haven't already. So go ahead to python.org. Let's go to downloads, and it should recognize what operating system that you're on. And you can just go ahead and hit the download button and then follow the steps to download this. I've already got it downloaded, so I'm not going to walk through this. Okay, great. Now that we have Python installed, one of the other amazing things about VS Code is you can actually open a terminal up inside of Visual Studio Code. The way you can open your own terminal, if this is your VS Code, you can go over on this top bar to Terminal and select New Terminal. And you'll see something that looks like this. It might be a bash, it might be a ZCH, it might be a PowerShell. There's a lot of different types of terminals that you'll be able to see by looking right here. We can now test to see if Python is installed correctly. If we type in Python space -- version, we should get something that looks like this. The exact version of Python doesn't really matter here, but ideally you're at least on Python 3.8. If Python dash dash version doesn't work, you could also try Python 3 dash dash version. Now, if neither one of those works, we actually have a number of troubleshooting tips in the GitHub repository for this course. And oftentimes, a quick Google search on whatever error that you have, you'll get a link which will lead you to the answer. But if that Google search doesn't lead you to the answer, then just go ahead and drop an issue or a conversation associated with your issue on the GitHub repo associated with this course. In particular, there are a couple of common errors that I've definitely seen a number of times. So if you see an issue on your instance that matches something on the screen here, definitely 100% be sure to check out those troubleshooting tips. Sometimes just installing some of these applications is really the hardest part of doing the entire coding journey here. So please make sure you have Python and VS Code installed correctly before moving on. And don't be discouraged if this doesn't work exactly the way that it should right away. Now, if you're on a Mac, you can actually hit Control backtick and it will toggle back and forth between having the terminal open and closing it. I find this really helpful and I use it all the time instead of hitting the buttons. A key tip for productivity is going to be using keyboard shortcuts instead of clicking around all the time. You'll be much faster. Okay, great. We have Python installed. We have Python and Solidity extensions of Visual Studio Code installed. Let's start working on a new project. So in our terminal, we can create some folder. I've already created a demos folder here. You can create one as well if you'd like by doing mkdir demos. Since I've already done it, the file already exists, and then cd into demos. You can type clear, or if you're on a Mac, Command K to clear the terminal. Now, here's what we're going to be doing. We're going to be working with simple storage again, the exact same contracts, but instead we're going to be using web3.py. So we're going to make a new directory inside of our demos folder / directory called web3.py simple storage, and we're going to cd into this new folder right here. Now, again, all the completed code is going to be in our GitHub, and there's going to be a link to everything that we do in this folder in this GitHub. So you can always refer to that if you get lost. And the next thing that we want to do is we want to have our Visual Studio Code know that we're in this folder. So we can go ahead and click this files icon and hit open folder. And I'm just going to go to this web3.py simple storage and hit open. And another VS Code will actually pop up. And we can see on the left-hand side here, we have a folder. This will show all the different files and folders in our web3.py simple storage directory. Let's go ahead and create a file .sol. We can right-click on this area and select New File and do simple storage.sol. And then we can go back to our simple storage.sol in Remix, copy everything, and then paste it into here. If you don't have it up, remember you can always refer back to the GitHub repository, which will have it in there for you. Awesome. Now we have our Solidity in its own file called simplestorage.sol. You'll notice that some of the words are actually highlighted different colors. This is known as syntax highlighting, and it's due to the fact that we added the Solidity extension in. It makes reading this code a lot easier. Now that this file is in here, we'll see that we have this little dot here. Whenever you see this little dot, this means that your VS Code file isn't saved. So we want to always save it. Otherwise, when we compile or we go to run a script, things might not work correctly. So we can save it by going up to File and then selecting Save. Or again, you're going to want to learn how to do the keyboard shortcuts because you're going to want to hit Save often. For Mac, it's Command S. And for Windows, it's Control S. Now, the other thing that you'll see is you get this red line here. This is VS Code's way of telling us it thinks that there's an error at this position. So this is really just the extension being a little bit confused here. And we can safely ignore this. And normally when I'm coding, I do just ignore it. We're often going to be flipping back and forth between compiler versions. So oftentimes this isn't really a helpful warning here. But if it is really bothersome, you could right click it and do something like Solidity change global compiler version, or we can go to Code, Preferences, Settings. Let's close this so we can see some more things in here. We'll look up Solidity and we'll come to this Solidity extension config. What we can do then is scroll down and we can see Solidity compile using remote version. This will allow us to choose what version we want to compile with. If we do 0.6.0 and hit save and go back to simple storage, you'll see the red line is now gone. While we have this up, another really helpful piece that we can do here is we can add what's called a formatter. So if we scroll down to Solidity Formatter, you'll see that this enables/disables the Solidity Formatter. We can go from none to prettier. Then we'll also look up format on save, and we want to make sure we have this editor format on save checkmarked. What we can do then is we can come over to simplestorage.sol, and maybe I've got some bad formatting in here. We'll move over favorite number, string name, and put a whole bunch of new spaces in here or something. Now, if I hit save, it automatically reformats our file to look a lot nicer. So to recap, we want to turn on format on save. And if you get issues with a red line under Pragma Solidity, you can just change the compiler version in your settings here. Now, while we're in here, we're also going to go ahead and set up our Python formatting as well. So the first thing that we're going to do is we're going to install the black Python formatter. So we're going to open up our terminal here. And whenever you install Python, it comes pre-installed with this package called pip. To check to see if you have pip installed correctly, run pip -- version. Now we can install the black formatter by running pip install black. I already have it installed, so it's going to be pretty quick for me. Then we'll come to our settings and we'll look up Python formatting, and we'll scroll down to Python formatting provider. You might have AutoPep8 or none in here. You're going to want to change it to black. This way, whenever we save our Python files now, they will also get automatically formatted to be very readable and really nice. And just to note, for my demos in Solidity, I don't always have format on save for Solidity. I do have format on save for my Python, but I'm still going to highly recommend you have format on save for both your Python and for your Solidity anyways. So how are we going to actually deploy this? Well, this is where our Python is going to come into play. Let's go ahead and create a new file on the left here, and we'll call it deploy.py. Now let's go into this deploy.py file, and let's start actually figuring out how we can deploy this in Python. And this is the part of the course where we start using Python here. If you're unfamiliar with Python or a little bit weaker on Python, there is a fantastic free code camp course that goes through all the basics of Python. If you want to learn more, I definitely recommend checking it out. However, we are going to walk you through all the scripts that we write anyways, so don't be afraid to just jump in and follow along with what we're doing here, even if you have no experience. So the first thing that we're going to want to actually do is read this simple storage Solidity file. We need to get this into this deploy script so that our Python file knows what it's going to deploy. So how do we do this? Well, we're going to type with open quote / simplestorage.sol, comma r, as file, simple storage file equals file.read. Now, what is this actually doing? Well, it's saying that we're going to execute some code inside this indented area after the colon. And then once this code is finished, we're actually going to close this file. Because right now we're opening it, we're going to close it once it's done. The file that we're going to open is going to be this simplestorage.sol, which is located right here in this same directory that we're in. We're going to only read from it, and we're going to call it file. And then we're going to read all the contents of this file and place it in a variable simple storage file. So then we can go ahead and write a print statement, print simple storage file. And if you hit save here, you'll see that it automatically gets formatted, which is really nice. If you want to run black yourself, you can just type black dot, and it'll automatically format all the Python files in your folder here. You'll know that you're doing it right if you add a whole bunch of new lines and then save it. Anyways, enough on formatting. Let's head on down to the terminal and let's call Python deploy.py. And we can see our terminal printed everything in simple storage file, which is perfect. Now our Python script has what it needs to actually get started working with our Solidity. Now, something you'll see I do a lot is I save a lot. And if you're looking for some keyboard shortcuts, you can always do Command P, add a little bracket here, and look up keyboard shortcuts reference, and click this. And it'll bring you to this keyboard's reference page based off of what operating system that you have. All right, great. So now that we can actually read from our simplestorage.sol file, we actually have to compile it. Because remember, back in Remix, every single time we did anything with our files, we had to compile them first. So we need some compiler in Python. Luckily, there is a fantastic Python package called PySulkX that does exactly this. Now, I also want to point out though that PySulkX is actually a fork of this package called PySulk. Now, you can still use PySulk. However, I'm going to highly recommend that you use PySulkX instead, as PySulkX is a lot more actively maintained than Ethereum PySulk. We can install it with pip install PySulkX. We could even hit this little copy button, move back on over here, paste it in, and hit enter. Again, I've already installed it, so it's pretty quick for me. The way that we can use it now is by importing it into our Python here. So we'll say from sulkx import compile standard. Compile standard is going to be this main function that we actually use to compile this code. So let's go ahead and compile our Solidity. We're going to save our compiled code to a variable called compiled sol. And this is going to be equal to us calling this compile standard function, but we're going to add a lot of variables and a lot of parameters into this function here. First thing we have to add is a language, which in this case is Solidity. We're going to add in some sources, which we're going to say our sources is going to be simple storage.sol, and it's going to have some content, which is equal to this simple storage file variable that we made. Oh, excuse me. This all has to be in a bracket piece as well. And see, if I hit save here, it auto formats, which is really nice. And another quick tip, you can see how even my brackets are highlighted in these fun colors. If we go down to extensions and look up bracket, you can add this bracket pair colorizer, which will help make the brackets look a little bit nicer, kind of as you see here. You can go ahead and install that as well. Anyways, then we'll add some settings. And a lot of this is a little bit lower level stuff than what you're really going to have to know or use. So I'm not going to go too deep into everything that's actually going on here for now. But in our settings, we're going to choose an output selection, which is going to choose what we output when we compile this. We do a little star here. And in the star, we're going to do another star. We're going to choose our output list. We're going to get an ABI out. That's incredibly important, which we've talked about before. We're going to get some metadata. We're going to get an evm.bytecode. We're going to get an evm.sourcemap. That's pretty much it. Again, I'm not going to go too deep into what this output selection and what these settings are actually doing. But if you want to learn more, you can go to the homepage of PySulkX, scroll down to the documentation section, and read more in the docs on what you can actually put and all the different features that this actually has. The last thing we're going to do is we're going to add a Sulk version or Solidity version. We're going to say Sulk version equals, and then we'll choose the version that we want to use. So we'll put in 0.6.0. And then what we should be able to do is print out this compiled sol, and we'll see just a whole bunch of really low level stuff. So let's go ahead and run this. We'll run Python deploy.py, and you'll see we get this massive object here, which has a whole bunch of basically unreadable pieces. But this is a lot of the low-level code that actually gets compiled whenever we use the compiler in Remix or now in Python. Remix actually does the exact same thing. Once we compile something on Remix, you can actually copy the bytecode. If you hit this little copy button and copy the bytecode and come back to your VS Code and create a new file, a keyboard shortcut to create a new file is Command N, and we paste everything, we can see there's a whole bunch of stuff in here. These opcodes are the low-level code that our contract is actually doing, that actually governs how this code works. This is what our written code is getting compiled down to, so Solidity can actually read it and understand what's going on. You'll also see this thing called ABI, which is in Remix, and we're even going to output it right here. We have this ABI thing. Now in Remix, if you hit copy the button on the ABI, come back, create a new file, paste it, you can see we have this long JSON object. This is that application binary interface that we've talked about so much. You can see that it's actually describing all the functions and variables. So for example, we have a function called addPerson, and it takes two parameters, a name and a favorite number. So we have this input section for the function, and we have this section that describes what the function is actually doing. So the name is addPerson, It doesn't have a return type, it's non-payable, and it's a function. And we can see that for pretty much everything in here. This is the lowest digestible way to say, hey, here's what all the functions are, here's what the parameter types are, here's what the return types are going to be, and everything like that. So we're going to close it out for now, though. So this is fantastic. We've now compiled our Solidity. Typically, I usually also like to output it and print it out to a file as well. So to do that, we'll do with open compiled code.json. And this time, instead of reading, we're going to write, and we'll call this as file as well. Instead of doing file.write, we're going to do what's called a json.dump. Compiled sol file. We do need, of course, to import JSON. Also, just to note, I know it says we're using Sulk here, but please use Sulk X still. I ended up filming a little bit of both versions, so I did a little bit of a mix and match, but please use Sulk X even if you see Sulk. What this line is going to do is it's going to take our compiled sol JSON variable and just dump it into this file here. But it's going to keep it in the JSON syntax, so it's still going to be JSON-y. So now if we run python deploy.py, we'll see we have a new file in here called compilecode.json. The other reason that I wanted to do this was because if I hit Control S, it actually formats this into a readable way. Now again, we can go into these settings here. We can look up JSON and we can do enable JSON formatter. And this will automatically make it so that we format this JSON so it's a lot more readable. Again, the reason I like to output this is because this ABI is so important and we're going to use it so much that I like to kind of be able to see it and read through it really quickly. The rest of this lower level stuff like EVM and bytecodes and opcodes, we don't really work with so much. However, as you learn more and more about Solidity, you'll probably see more and more of opcodes. So if you really want to learn a lot of really low level stuff, look into opcodes, but for the purpose of this tutorial, we're not going to be going too deep into it. Okay, awesome. So we've compiled our Solidity. We've even stored our Solidity code to this compiled code.json file. Now what do? We probably want to deploy it and test it out. So how do we actually do that? Well, first, we actually have to get the bytecode. We need the bytecode of the file so that we can actually deploy it. So we're going to do bytecode equals compiled sol contracts simple storage.sol simple storage EVM bytecode object. All right, great. There we go. So now we have our bytecode. We also need to get our ABI. So we need to get the ABI. So what we're doing here when we're typing in all these words like contract, simple storage, is we're walking down the JSON here. So when we say we want to get the bytecode, in this compiled Solidity JSON, we want to go to contracts, simple storage, EVM bytecode. So contracts, inside this contracts JSON, we got to go to simple storage. Inside this simple storage.sol, there's another simple storage. Inside that, there's an ABI, but that's not what we want. We want the EVM. So we're going to scroll down. Aha, we're going to get the EVM. Then what do we want? Then we want the bytecode. Great. And then we want the object. So this is the bytecode of our contract. It's the really low level stuff that the Ethereum virtual machine or the EVM is going to understand. Now we also need the ABI. When we deploy this to a chain, this is what we're going to need. We're going to need the bytecode and the ABI. The ABI we can, of course, get from this kind of same method here. So to get this, we can do ABI equals compiled sol, same thing, contracts, simple storage.sol, simple storage, and as you can see, we're right here, and then we can just grab this ABI object. ABI. And we can even do print ABI, we'll do Python, develop.py, and indeed, our ABI is printed here. Awesome. So now that we have our two main pieces to deploy this, now all we have to do is deploy it. But the question then becomes is where are we going to deploy it to? Which blockchain are we going to deploy it to? In Remix, when we were first playing around, we were using a JavaScript VM or a fake or a simulated environment. We absolutely could, and we absolutely will learn to deploy this to a testnet, because that's going to be the same way that we're going to deploy it to a mainnet. But before we do that, we should learn how to deploy this on a simulated environment or something similar to that JavaScript VM, so it's much faster and easier to test things. And this is where Ganache is going to come to the rescue. Ganache is a simulated or a fake blockchain that we can actually use to deploy our smart contracts to and have it interact like it's a real blockchain. Ganache is going to allow us to spin up our own local blockchain. And it'll look something like this. Now, the user interface is really nice because it allows us to kind of do this one-click blockchain to create our own local blockchain. That means that this blockchain isn't connected to any other blockchain out there, but it'll act like a blockchain. But it'll be a lot faster than us having to interact with a testnet, and we control the entire blockchain because it's only one node. We're the only node. So Ganache, great way to test things quickly. Now, we're going to mainly be working with the user interface, but I'm also going to show you how to work with the Ganache command line. You can really use either one depending on what you want to do, but a lot of the tools actually have built-in Ganache command lines, so it's definitely really useful to learn that as well. So again, Ganache is going to be our simulated environment here. So what we're going to do, once we get into Ganache, we can just go ahead and hit Quick Start. This will automatically upload and get started with our own local fake blockchain. You can even see it gives us some accounts. This should look pretty familiar. It should look very MetaMask-y, right? We have an address here, and each one of these addresses has a private key. In your Ganache, you can go ahead and just click the key and hit Show Keys, and it'll show you the account address and the private key. But of course, these are for development purposes only. Each one of these accounts has a balance associated with it. We can see a mnemonic or your secret phrase. You can see blocks, transactions, and a whole lot of other really useful features here. And it even tells us how to connect to this blockchain. And these are the connecting features that we're going to want to use. Let's learn how to connect to this Ganache blockchain from this user interface first, and then we'll learn how to do the command line version. This is when we finally start working with web3.py. You can just do pip install web3. And now we can start working with web3.py. Right at the top, a little confusingly, we're going to do import web3 from web3. Whoops, and this should be from web3, import web3. Sorry about that. Now, to connect to this blockchain, we choose what's called an HTTP provider. If we look at this Ganache instance, we have this RPC server, which has this URL, HTTP 0.0.0.854. This is the URL that we're going to use to connect to this blockchain. In Remix, we're actually using our MetaMasks directly to connect to the blockchain. However, we want to connect directly to our simulated, our fake blockchain right here. So what we're going to do is we're going to do W3 for connecting to Ganache. W3 equals web3, web3.http provider of HTTP 0.0.0.0, and it was on port 845. Port 845. Now, with everything that we show you, you're probably going to want to get really familiar with the documentation because even after being a pro, you're going to want to use it more and more. If you want to learn more about other providers, you can go to the providers page of the documentation. The next thing that we're always going to need as well is we're going to need the chain ID or the network ID. What is the ID of this blockchain? And for Ganache, it's 1337. It's supposed to be a funny leet reference. So we'll do chain ID equals 1337. Now, we're also going to need an address to deploy from. We can go ahead and grab one of these fake addresses in here to work with. Similar to how in Remix, when we were working with the JavaScript VM, we were given a bunch of fake addresses. We're doing the same thing, but with Ganache. And then we're also, of course, going to want a private key. We need the private key, of course, to sign our transactions. So we'll do private key equals this. Now, just note, whenever you import a private key in Python, you need to add an OX to the front. Python is always going to look for the hexadecimal version of the private key. Awesome. Now we have all the parameters that we need for interacting with and connecting to our Ganache local chain. It's time to finally deploy our simple storage.sol contract. Let's do it. So to create a contract that we're going to deploy with web3.py, we're going to do simple storage. We're going to call this variable w3.eth.contract. And we're going to give it ABI equals ABI and bytecode equals bytecode. Great. Does this mean we've deployed it? Well, no. This just means we have a contract down. So we can do print simple storage, and you'll see if we run python deploy.py, you'll see we have a new type here, class web3.utils.datatype.contract. This is another type that if you want to learn more, you should definitely check out the web3.py documentation. So we have a contract object. Awesome. How do we actually deploy this? Well, we need to actually build our transaction. Because again, whenever we interact with the blockchain, whenever we make a state change, and in this case, we'd be deploying a contract, we're going to make a state change. So we first need to build a transaction, sign a transaction, and then send a transaction. And to do that, we need to talk about that nonce thing again. Remember way back in our blockchain demo, when we used a nonce to solve the answer to that really difficult mining problem? Well, the definition of nonce is just a word coined or used for just one occasion. And in cryptography, it's an arbitrary number that can be used just once in a cryptographic communication. So this nonce that's used to find the answer is going to be different from another nonce that we're actually going to need to make our transaction. See, if we look at our MetaMask and we look at our activity, and we look at one of the transactions we've made recently on Etherscan, if we scroll down, we'll see nonce here as well. This nonce is the number of transactions that our account has actually made. Every time we make another transaction, our transaction is hashed with a new nonce. This is what's going on behind the scenes with our transaction. And we need this to send our transaction. We can actually get our nonce by just grabbing our latest transaction count. Get the latest transaction. We can do nonce equals w3.eth.get transaction count, and we'll put in my address. This will give us the number of transactions, and it'll effectively give us our nonce. We can even test it out with a print. Python deploy.py. We can see that the answer is 0, because on our local blockchain, this address that we're using hasn't been used before. We can even go to the transactions tab, and we can see that there are no transactions that have ever occurred on our local blockchain. Now, to deploy this contract, we need to make a transaction. Remember, everything that we do, every time we change the state of a blockchain, we're going to do it in a transaction. Let's create a transaction object. To do this, we can do transaction equals simple storage, which again is this contract object, dot constructor dot build transaction. Now, as you might have pointed out, our simple storage.sol doesn't actually have a constructor. Every contract technically has a constructor. This one's is just blank. We're not telling our simple storage.sol to do anything. We saw back in our fundme example that the fundme example does have a constructor. So now we want to put in some parameters for this transaction. In web3.py, we always have to give at least a couple of parameters. We always have to give the chain ID, which we already got from above, which is 1337. So we can just do chain ID. We need a from address, in this case, my address. And then we need a nonce, which in our case is just nonce. Great. Now we have a transaction object. Let's even print this out and see what it looks like. Whoa, what's this? We can see there's even more parameters in here than just what we made. So we have value, which is the ether or the Ethereum that we're going to send. We have gas. We have our gas price, which we could arbitrarily set if we'd like. We have the chain ID. We have from address. We have the nonce. And then we have this giant data object. And then 2 is just empty because it's sending it to the blockchain. This giant data object here is encompassing everything that's happening in this simple storage.sol. Now, that's just a transaction, and anybody could actually send this transaction as long as it's signed by them. So we have this transaction, but we need to sign it from somebody. Since we're sending it from our address, our private key is going to be the only key that's going to work to sign this. Remember back when we were talking about public and private keys, we right now have a message that is defining how to deploy simple storage, but it's not signed yet. So we're going to need to use our private key to sign it to create this unique message signature that we're the only ones that can create the private key, but anybody else can verify that it was us who signed it. So now signed transaction equals web3.eth.account.sign transaction, and the parameters it takes are going to be transaction and then private key. We're going to say the private key equals private key. Because above, we've actually gone ahead and added our private key in here. Now guys, a really, really important note about putting your private key in your code. This is really bad practice. If you push this to source or you push this to GitHub, somebody else can see your private key and steal all your funds. So we don't want to hard code our private keys in our code like we're doing here. So let's take this time to talk about environment variables and how to set them. Environment variables are variables that you can set and that we set in our terminal and in our command lines. The following is a way to set an environment variable in macOS and Linux only. Don't worry, we'll show a way to make an environment variable in Windows as well. You can set an environment variable by running something like export private key equals, and then adding whatever variable that you want. Now, if you type echo $private key, this variable actually shows up. To set environment variables with Windows, the process that we're going to do is actually a little bit different. I've left a link in our GitHub to actually set environment variables in a Windows setting. And we've left a couple of really helpful links for working more with environment variables. You should definitely check them out. It's important to note that this export method that we're doing here for creating environment variables only works for the duration that our shell is live. So if we were to close out of our shell and then reopen it, our environment variable that we set would be gone. So we'd have to rerun that export command. We're going to show you a way to set environment variables so that you don't have to keep doing that. Now, it's also not great to have it in plain text on your computer. However, it's a lot better than hard coding it into our script here. Now, remember, if you're using an account that has real money in it, which I highly recommend you do not do, don't send this environment variable or this private key or any of this code anywhere, because then people can steal all your funds. Once we move to Brownie, we'll show you a more effective way for private key management. But for now, be cautious here. But if you followed along and set up a brand new account that has no real money and only test that money in it, then great. Who cares? Because it's test and it's fake money anyways. I think I've talked about it enough. Anyways, let's get back to it. We can actually access this environment variable in Python using os.getEnv. We just need to import OS. And now we can access our private key in our script without actually hard coding it in. Let's see what happens if we do print private key, python deploy.py. You can see our Python script was able to pull our private key from our environment variable. The other thing that we can do is create a .env file. A .env file is typically where people store environment variables. It's important to not push these to source if this is what you're going to do. In this .env file, in Python, we can just do export private key, and then same as what we did before, add the 0x at the start, and then private key. So we could put 100 environment variables in here. Export some other var equals 7. If you're going to do it in this way, please, please, please always set a .gitignore and make sure .env is in here. This will help make it harder for you to accidentally push your .env folder or your .env file to GitHub. Python actually has a way of loading directly from a .env file without having to export our environment variables or run source.env or export or really anything. And we can do it with this python.env package. If we close our shell and then reopen it, if we run echo some other var, we're going to get none here. And in fact, if we run python develop.py, when we print this environment variable, we're going to get none. However, we can use this .env to have it pulled directly from our .env. So we just do pip install python.env. I've already downloaded it, so it just says requirement already satisfied. And then what we can do at the top of this, we can do from .env import load.env, and we can run a load.env function right at the top. This load.env looks for this .env file and automatically imports it into our script. So if we run this now, you'll see that the environment variable was successfully imported into our script, and now we can use it. So let's use it, for example, with our private key. Private key equals os.getEnv. Private key. Now we can even print it out just to test. We'll run our script, and awesome. We can see our private key is being successfully pulled in, and we didn't hard code it into our application. All right, let's get back down to our signed transaction here. Now let's go ahead, print this out, and take a look at what this looks like. Now we can run our script, and great. What we see here is an example of a signed transaction. Remember, this is exactly what's happening when we were looking back at public-private keys. We are signing a transaction that is actually deploying a contract to the blockchain that anybody can easily verify. All right, so we finally have our signed transaction. Now we want to send this to the blockchain so it actually can deploy. Let's send this signed transaction. We can do transaction hash equals web3.eth. Here's a little helpful tip. If you see this little box underneath with suggestions show up and you just hit tab, it'll auto-complete the rest of your text here. .send raw transaction, and we'll give it our signed transaction dot raw transaction. This will send our transaction to the blockchain. Now, if we look at our local ganache and we look at transactions right now, it'll be empty. But let's see what happens when we run this script. Okay, so we didn't print anything out, but if we go to our ganache, we can see that a transaction actually did go through. It was from the address that we put in here. We created a contract at this address. This is how much gas it used, and this is how much value was sent with it. We can even click on it to see more information about this. Now, this is the other advantage of doing this locally, is that the transaction automatically went through. We've sent our first transaction to a local blockchain, and this transaction is deploying a contract. Great work. You can already see how much faster this is than working with a testnet. One other thing that's really good practice whenever sending a transaction is we wait for some block confirmations to happen. So we can do transaction receipt equals web3.eth.wait for transaction receipt tx hash. This will have our code stop and wait for this transaction hash to go through. Awesome. So I just ran it again. And if we go to transactions, we can now see that there are 2 transactions here. And our code waited a little bit longer for this one to complete. So, of course, we've deployed a contract, but how do we actually interact and work with the contract? Let's start doing that. So, when working with contracts and we're working with on-chain, whenever we work with a contract, we always need 2 things. We need the contract address and the contract ABI. Oftentimes, if you're looking for a specific ABI of a type of contract, you can usually just Google it. So we need to make a new contract object to work with contracts. Let's go ahead and create this simple storage contract so that we can actually interact with it. So we'll do simple storage equals w3.eth.contract. Now we need our address, which we can get from Ganache, but that might be a little bit hard to always be checking the blockchain for a transaction. It's actually also in this transaction receipt. Address equals transaction receipt dot contract address. And then, since we've compiled this, we also have our ABI already. ABI equals ABI. Sometimes you'll see people have a file called abis.py or abis.json or something like that, and they'll load ABIs in directly from there. And great, now that we have the address and the ABI, we can start interacting with this contract exactly as we did in Remix. So let's do a print statement to get that initial value that is returned from our retrieve function. Remember, it should be initialized to 0. So if we do print simple storage dot functions dot retrieve, let's see what happens here. Huh? What's this? We get this function retrieve bound to in these parentheses here. So what's going on? When making transactions on the blockchain, there's actually two different ways that we can interact with them. We can interact with a call, or we can interact with a transact. When we use a call, this is just to simulate making the call and getting a return value. Calls don't make a state change to the blockchain. And it's similar to how in Remix, we would call these blue buttons and nothing on the blockchain would actually change. We can actually also call these orange buttons or these non-view functions and just not actually make a state change. Remix defaults these blue buttons to be calls and these orange buttons to be transacts. In Python, we can actually pick which one we want to do. A transact call is when we actually make a state change. And this is when we actually have to build a transaction and send a transaction. You can always just call a function no matter what that function is, but just keep in mind you won't make a state change. You can also always transact on a function even if it's just a view, and this will attempt to make a state change. Something like retrieve, even if we transact on it, it won't make a state change. So for something like retrieve, where we don't actually want to make a state change, we just use the call function. So we'll just do .call. Now, if we try to run this, you'll see we do get the 0 because now we're actually calling this transaction. Awesome. So now we have our initial value for our retrieve function. Let's keep going. Let's try to update this favorite number using this store function. This, we'll just keep in mind, is our initial value of favorite number. We know that this store function is orange and will actually make a transaction. But if we wanted to, we can even just use call on it. We'll do simple storage .functions .store, and we'll put that 15 in here .call. Let's see what happens when we send this. You can see it returned a blank. That's because this store function has no return type. If we give this returns UN256, and then we say return favorite number, and now we go back here and we run this again, you'll see now that we get a 15 back. If we go to Ganache, you'll see that we keep making a whole bunch of different contracts, but none of these are contract interactions. That's because when we call a function, we just simulate working with it. If we call retrieve again right afterwards, you'll see that it's still 0. It's because calling is just a simulation. Now let's delete all that. So let's actually build a new transaction to actually store some value into this contract. Since we want to make a transaction, we got to go through the same process as when we deployed this contract. Let's first create a transaction. We'll call it store transaction equals simple storage .functions .store, and we'll give it some number, in this case 15. And then we have to do .build transaction, and we'll put those same pieces in here from before. We're going to have chain ID be the chain ID. We're going to need from, going to be my address. Nonce is going to be the nonce plus 1. We're going to need to do nonce plus 1 because we actually used this nonce already when we create our initial transaction. Remember, a nonce can only be used once for each transaction. So this transaction is going to have a different nonce than the nonce we use to deploy the contract. Now that we have the transaction, let's go ahead and sign it. We'll do signed store tx, and we'll do web3.eth.account.sign transaction store transaction, and then private key equals private key, and we'll go ahead and save. Then, of course, we need to send it. So we'll do transaction hash equals w3.eth.send_raw transaction signed store transaction .raw transaction. And let's grab that transaction receipt again by doing transaction receipt equals w3.eth dot wait for transaction receipt. And actually, let's call this send store tx. That wait for receipt, send store tx. Awesome. It looks like we're following the same steps here as we did above. We created the transaction, we signed the transaction, and then we send the transaction. Down here, we create a transaction, we signed the transaction, we sent the transaction, and then we waited for the transaction to finish. So let's run this. All right, great. We still have this print function printing out the current value of retrieve. Let's go over to Ganache and see if there's anything different here. There is. Instead of all these contract creations here, we now have a contract call. We can see there's some transaction data that was sent, a different amount of gas, same gas prices. However, this actually updated and sent the transaction to our blockchain. Now, if we call this retrieve function again, this should print out our newly updated value, which in this case was 15. Let's go ahead and run Python deploy.py, and we can see it started at 0, and then it turned to 15. Awesome. We've made our first state change to a contract that we've deployed on our local blockchain. Great work. Sometimes it's nice to put some lines in here to tell you what's going on, to make it a little bit more clear. So I'll put something like deploying contract, ... right before we deploy our contract. After we do it, I might do deployed. Then, right before we update our contract, we'll print out something like updating contract. And then, right after it's done, maybe something like updated. Now, if we run this now, you'll see as this goes along, we'll get these things printed out saying deploying contract, contract, deployed, updating contract, updated. This will make those moments when waiting for these contracts to actually finish a lot easier. You're doing fantastic. So Ganache user interface is really nice because we can see a lot of things that are going on here. However, it's a little tricky to do a lot of programmatic stuff. Oftentimes, engineer will use what's called a command line interface of Ganache instead of the UI. So we're going to go ahead and close this out, and we're going to use the Ganache CLI instead of that user interface that we just saw. And this is what Brown is going to use on the back end when we move to Brownie. Let's learn how to actually do that. So in order to use the Ganache CLI or command line interface, the first thing that we need to do is download Node.js. Yes, I know this is a Python video. However, we do need to install Node.js to work with the Ganache CLI. You can come to this download page and choose your operating system and download it accordingly. We have a link to a video showing you how to do this in the GitHub. You'll know you've done it right if you can run node -- version in your command line and you get a version. It might be 12, might be 14, might be something else, depending on what version you downloaded. Next, we're actually going to install Yarn. Yarn is a package manager similar to pip and will allow us to actually download pieces and packages like the Ganache CLI from the package repository. We can install it with npm install -- global yarn. And you'll know you've done it right if you can run yarn -- version in your command line and you get the version outputted here. Then we want to install the actual Ganache CLI. We're going to be installing it with yarn. So to install this, we're going to do yarn global add Ganache CLI. This will install our Ganache CLI as a global command in our terminal. We can test to see if we've done it right. If we can run Ganache CLI -- version. Perfect. We now have the Ganache CLI. Let's spin up a Ganache chain with the CLI. If you have your Ganache UI open right now, please close it. Otherwise, it'll conflict. So to run a local blockchain from the command line, all you need to do is run Ganache CLI. And the node will start running directly in your terminal. If you scroll up, you can see a lot of familiar pieces. We see the available accounts, just like on the UI. These are the different addresses. And then we see a whole bunch of different private keys. This ganache spins up with a bunch of random addresses and random private keys. If we want it to always spin up with the exact same private keys so we don't have to update our private key every time, we can do ganache CLI dash dash deterministic. This way, we'll always get the exact same private keys and the exact same addresses. You can check out the documentation to see a bunch of other flags that you can use to run this. And you can see it's listening on 127.0.0.1. 127.0.0.1 is also known as the loopback address or localhost. Now, to work with ganache in the command line, all we need to do now is update our private keys and our addresses. Let's also update the HTTP provider, since now we're going to be looking at the loopback address. For my address, we'll scroll up to this top address here, and we'll place it in. And for our private key, we're going to copy this and put it into our .env file. It already has the OX at the top here. Great, now let's open up a new terminal. You can open up a new terminal by hitting this plus button here. And you can flip back and forth by hitting this drop down and flipping back to the ganache terminal. Now let's go ahead and run Python deploy.py. We can see the exact same output as we got when working with the UI. And if we flip over to the command line, we can see we've made a whole bunch of different calls to our blockchain. Each one of these calls is a specific JSON RPC call to our blockchain that we're making to interact with it. We can see information about the transactions that we sent. This one creates our simple storage contract. This one updates our simple storage contract. And great, you now know how to work with the Ganache CLI and the Ganache UI. Fantastic. So how do we actually deploy this to a testnet or a real network? When we're working with Remix, all we had to do was switch to injected Web3, and we used our MetaMask as our blockchain connection. Well, in our script here, we don't have MetaMask natively with our script. So we need some way to connect to the blockchain. We can see that when we're connecting to our own local blockchain, we just use an RPC URL that connects to our local blockchain. To connect to a testnet or to a mainnet, we can actually do the exact same thing. All we have to do is swap this out with the URL that connects us to a mainnet or a testnet. We can also run our own blockchain node, similar to how we're running our own local blockchain node. We can run a node that actually connects to a real blockchain. However, it's not always practical or really easy to do this. So sometimes we want to use an external or a third-party client that actually will run our blockchain for us. Let's learn a little about Infura. Infura.io is an application that will give you a blockchain URL for you to connect with, for you to run whatever you want to run. And you can get started for free. Let's go ahead and register. Then we just check our email, confirm email address, and awesome. Now we're inside of Infura. There's a couple other services out there that you can also check out, like Alchemy, which is another fantastic blockchain as a service platform. Infura is a freemium service. It starts out as free. If you make too many API calls or too many calls to the URL, they'll start charging you. But we can create a project for free for now. Let's go ahead, hit the Ethereum tab, hit Create Project. We'll call this Free Code Camp Brownie. Hit Create. Now we'll have a whole bunch of project keys and project secrets. We also have this endpoint section as well. This is how we're going to be deploying to the different networks. We can see we have an Ethereum mainnet connection, as well as Ropsten, Kovan, Rinkeby, and Gorilli testnets. There's also Polygon in here as well. Since we want to test and deploy to a Rinkeby chain, we can go ahead and move to Rinkeby. And then we can copy this URL. Back in our application, all we have to do is swap this out for the new URL. We also have to change the chain ID, our address, and the private key. If you ever are confused as to what is the chain ID of the chain that you're working on, you can always check this chainid.network, or you can usually ask somebody. Let's look up Rinkeby. We see the chain ID is 4. So we'll grab 4 and we'll place that in our script. Now this address and the private key that we gave it, aren't going to have any testnet Rinkeby in them. So we need to go in our MetaMask and grab the address, place that in for address, and then account details, export private key, type in our password, and grab the private key. Go into our .env file, leave the 0x, and replace the rest with